Hello everybody, welcome back to iBridge Chemistry. My name is Nihir and today in this video I will be covering structure 1.3. So I want to start with 3.1, emission spectra and energy levels. So let's start with talking about photon emission and how the lines are produced in the emission spectrum. So basically, atoms can absorb energy, right? And this energy can be from many different energy sources like heat or electricity. And as the atoms absorb energy, their electrons can jump from lower to higher energy levels. So the electrons can become excited, right? So they can move from the ground state, the stable ground state, to the unstable excited state. But as the excited state is unstable, electrons don't want to remain there, so they want to return back to their original position, so the lower energy levels, aka the ground state, from the higher ones, right? And in order to return back to the ground state from the excited state, the electrons must release the energy that they have absorbed to become excited. And this energy is released as photons. And this energy release is the reason why lines are produced in the emission spectrum. And the photons actually, like the energy of the photons, correspond to the energy difference between two energy levels. So let's say that an electron returned back to its ground state from like the second main energy level to the first energy level. So this is the ground state and this is the excited state. And the energy difference between them will actually correspond to the energy, and we can actually calculate the frequency with this equation. As we know, it's also given in the formula booklet. Okay, and also there is another equation, and this equation is also given in the formula booklet, and it can help us with understanding the relationships between energy, frequency, and wavelength of the lights. Okay, so let's take a look at the electromagnetic spectrum. So energy is inversely proportional to the wavelength. So this is an electromagnetic spectrum, and this is low energy and this is high energy, right? As we can see in the text here. So energy is increasing like this. So as we increase energy, as energy increases, because as we can see, this is the higher energy side and this is the lower energy side. So as energy increases, we can see how the wavelengths are actually getting smaller. So wavelengths are basically the difference between the two peaks, between the two peaks of the waves that are created. So as we can see here, when energy is low, the wavelengths are huge, but they're getting smaller as energy is getting higher, right? So here we can see how the wavelengths are so much smaller compared to the lower energy part, right? So as energy increases, so as energy gets greater, the wavelengths will become shorter. We can see how the wavelength is super short here, and how when there's lower energy, the wavelengths are longer. And this is how we can understand the inversely proportional relationship. And also energy and frequency, they're directly proportional to each other. So as we take, again, when we take a look at the electromagnetic spectrum, we can see in higher energy, there's a higher frequency. So frequency is basically, okay, I will be providing the full definition. So frequency is like the number of wave cycles that pass a given point per unit time. So as we can see, a lot of waves pass here. However, at a given point per unit time, only a single wave can pass here. But if we take a look at here, we can see that there are multiple waves that can pass, right? So as energy increases, we can also say that the frequency will increase. We can just understand this from the diagram. This is also provided, a similar one is also provided in the data booklet, as I remember. Yeah, so this explains the directly proportional relationship. Okay, So there are like different kinds of spectrum. So firstly, we have the continuous spectrum, and this is what a continuous spectrum looks like. So as we can see, the continuous spectrum actually contains all the wavelengths of visible light. So this is the visible light in the electromagnetic spectrum. And when we take a look at the continuous spectrum, we can see that every single wavelength of every single color can be seen. This is, by the way, the visible light section of the electromagnetic spectrum. And as we can see, it appears as a rainbow when passed through a prism. I think we're all familiar with this, and it is a smooth gradient. So the gradient is not actually interrupted in specific points, right? However, when we take a look at, however, when we take a look at line spectra, here are some examples of line spectra. This is the emission spectrum, and this is the absorption spectrum. So when we take a look at them, we can actually see how, for example, an emission spectra, how it contains discrete lines of specific wavelengths against a dark background. So this is the emission spectrum, it is a line spectrum, and we have the dark background, and we can actually see the discrete lines that were produced as a result of this like process, like electrons actually returning back to their ground state from their excited state. We can see how discrete lines appear against a dark background and how we can only see specific wavelengths. So when compared to the continuous spectrum, we can see all of the wavelengths, right? We can see all of the colors. But for example, in the emission spectrum, I think this is the emission spectrum of hydrogen. So when we take a look, we can only see this specific wavelength. We can only see this specific wavelength. But when we take a look at here, like for example, in the continuous spectrum, we had the yellow color, right? We can't see it. So there are only discrete lines that show the specific wavelengths. So lines, as I mentioned, line spectra are produced when electrons transition between quantized energy levels. So this is an example of emission spectrum, as I stated. We can see how bright lines correspond to wavelengths emitted. So it is when actually like it is when electrons return back to the ground state. It is when electrons return back to the ground state from their excited state. It is the spectrum that is produced. But on the other hand, absorption spectrum, here, this is the absorption spectrum, and we can see that there are some dark lines against the continuous rainbow background, and it actually is produced, this absorption spectrum is produced, and these specific dark lines are actually produced when electrons move from the ground state to the excited state. So these are basically, so if an electron falls back to the ground state, an emission spectrum will be produced. But if if electrons move from the ground state to the excited state, if it gets excited, an absorption spectrum is produced. So these are the differences between the three types of spectra. Okay, so now let's talk about the hydrogen emission spectrum. So as we know, hydrogen is a gaseous element, and when high voltage is applied to it, it can actually emit light, right? And when we pass the light that is emitted by hydrogen through a prism, this is the line spectrum. This is the emission line spectrum that it produces. So as we can remember from like the emission line spectrum, we can see that how there are series of distinct lines, and how each line corresponds to a specific wavelength of light. For example, here, the red line corresponds to the wavelength of 656 nanometers, right? We can see the wavelength values here. So, basically, this is what happens when hydrogen is actually subjected to high voltage, right? And we can see the distinct lines and how there are gaps, right? But how are these distinct lines produced, and why are they actually produced? So we know that the energy levels in hydrogen are quantized, right? And the electrons can only occupy specific discrete energy levels. right? So we have different like energy levels and they're quantized. So for example, an electron can be in the second main energy level, or it can be in the first main energy level, but it can't be in between these two energy levels. So this is like a staircase. This is like you can't stand you can't actually like you can't stand on any step, but you can stand on any step. So you can stand on n equals 2, or you can stand in n equals 1, but you can't actually stand between them, right? This is like the whole logic of this thing. And the electrons can only occupy specific energy levels, like steps on a staircase. Okay, so when electrons absorb the energy, they get excited and they're unstable. So as they're unstable, they fall back to a lower energy level and they release energy in the form of a photon. And as I mentioned earlier, this is the difference between the two energy levels. And these are the lines that correspond to the energy that is released by the electrons. And also, as we can see, how these lines actually become closer, or they converge at higher energies. This is how energy increases in the hydrogen emission spectrum. As we know, like purple has the highest energy. We can just take a look at our electromagnetic spectrum for this, and we can see how the discrete lines actually converge, because this is actually due to the reason that at higher energy levels, so as the principal quantum number increases, the energy levels themselves get closer. So when we, for example, draw the Bohr model as the main energy levels are further from the nucleus, they actually get closer. So this is how we would draw it. For example, if the distance is 1, here the distance must be 0.5, for example, because this is like how, this is the model, this is the whole logic of the model. Okay, so this is what it looks like. And we can actually link, we can actually link electron transitions to the spectral lines. And here we have some kind of like transitions, different kinds of transitions. So when an electron falls from a higher energy level to the first energy level, or the ground state, from like when it falls from any excited state to a ground state, so when it falls to n equals 1, it will be the transition that will emit the highest energy, right? And this will actually be, this transition will be in the UV region of the electromagnetic spectrum. And when an electron transition occurs from an excited state to n equals 2, the transition will be in the visible region of the electromagnetic spectrum. So we will be we can be able to see colors from these transitions, as the visible region in the electromagnetic spectrum could be seen with our eyes, and we could observe colors, right? Okay. And when an electron transition occurs between an excited state, a higher excited state, to the excited state of n equals 3, these transitions fall into the infrared region of the electromagnetic spectrum, and they actually emit infrared radiation. So this is kind of like, this kind of summarizes the whole thing, what happens when different types of electron transitions occur. Okay, so now I will be continuing with 3.3 main energy levels, and energy levels are the regions around nuclei where electrons are most likely to be found, and they basically hold electrons. So these are some examples of energy levels in the hydrogen atom. So they hold electrons. So as I mentioned, these energy levels are quantized, and the electrons can actually be inside them. They can't actually stand between them, right? Because they're quantized, like a staircase. Anyway, okay. It is like, you can just think of it as layers of an onion. And in order to calculate the maximum electron number that an energy level can hold, you can just use this. So for example, this is 2n2, 2n squared. And for example, if you want to find the maximum number of electrons that n equals the energy of n equals 3 holds, we can just put 3 here. So 2 times 9 will be equal to 18. So this is how you can calculate it. And these n's actually correspond to, these are, like, as you can see, some positive integers, and these are called a principal quantum number. So as the values get higher, they will actually be, it will actually show how the energy level is higher and it is farther from the nucleus. So for example, nucleus. So as we can see, this is n equals 3 and it is farther from the nucleus when compared to n equals 1, right? So these are the main energy levels. And this also like corresponds to the period number of an element. So for example, when we take a look at, what should we say? Let's take a look at beryllium, and it has 4 electrons, right? It has 4 protons and 4 electrons, so 1s2, 2s2. So it actually has, so it is actually in the second period of the periodic table. This can also show us the location of elements in the periodic table. And here you can see a little summary. And these were the principal quantum numbers, and as the radius gets larger, the energy is higher. So for example, n equals 2, the main energy level of n equals 2 has greater energy than n equals 1. And this is the ground state, as it's closest to the nucleus, and it has the lowest energy. Okay, so now that we have learned about main energy levels, now that we have talked about main energy levels, we can move on to sublevels and orbitals. So main energy levels are like they're kind of like the emperor, right? So it can be 1, it can be 2, it can be 3, but they're actually further divided into sublevels, and these sublevels can be S, P, D, or F depending on their shape. This actually depends on their shape. Okay, so main energy levels are further divided into sublevels, and this is how, and they actually increase in energy. So F has the highest energy and S has the lowest energy, and this is what it looks like. This is how we can see the relationship between them and their energies, whether if they're high or not. Oh, okay, so let's take a look at the first main energy level. So in the first main energy level, there is a single S sublevel, and the main energy level must be written in front of the sublevel. So this is the 1s sublevel, right? So let's take a look at the second main energy level. So within the second main energy level, we have the S and the P sublevel, and we must write the number of the main energy level in front of the letter of the sublevel. So this is how we can see it. This is how we can write it. So let's take a look at the third main energy level, and it has 3 sublevels: 3s, 3p, and 3d. And like similarly, the fourth main energy level has 4 sublevels: 4s, 4p, 4d, and 4f. So as you can see, there is a correlation between the number of sublevels that a main energy level has within it and its principal quantum number, which is n equals something, right? So 1 has 1, and it is S. So 2 has 2. I'm talking about main energy level here, 2 sublevels, and it is S and P. And the third main energy level has 3, and it is S, P, and D. And fourth main energy level has 4 sublevels within itself, and it will be S, P, D, and F sublevels. And also sublevels are further divided into orbitals, and orbitals are actually regions within subshells where there is a really high probability of finding an electron. This is a really important piece of information. Each orbital can actually hold a maximum of 2 electrons with opposite spins. Okay, so we have the s orbital, right? And the s orbital, the s sublevel, and the s sublevel actually has 1 orbital inside it. And as orbitals can hold a maximum of 2 electrons, its maximum electron number will be 2e, 2 electrons. And P is divided in, I wrote S. P is divided into 3 orbitals, px, py, and pz. And they all can hold 2, and when we add them up, it will hold a maximum of 6 electrons. And this is a similar thing with D. So D has actually 5 orbitals inside of it. And as each orbital can hold a maximum of 2 electrons, it will hold a maximum of, the sublevel can hold a maximum of 10 electrons. And this is the same thing with F. For F, it has 7 orbitals, and when we multiply 7 with 2, we have 14 electrons. It is like the maximum electron number. And this is how we can show it in a diagram. And also we have different orbital shapes. It can be spherical or the dumbbell shapes. So spherical is basically, this is how we draw it. We have our x, y, and z axis. And a spherical orbital is actually an s orbital, and we must just draw a circle. And also as the main energy level number increases, these s's get bigger. So for example, if 1s is like this, 2s will be bigger because this will be farther away from the nucleus, so its actual atomic radius will be larger. So size increases as the principal quantum number increases. So this is a spherical shape, and it is the shape of an s orbital. So we have the dumbbell shaped, and it is actually the shape of a p orbital. By the way, the d and the f orbitals shapes are not included in the curriculum, so that's why I'm not explaining it. Okay, so for the dumbbell shape, we actually have different kinds of ways of showing it. Different. We can show it in different axes. Okay. So firstly, we have the 2p x orbital, right? It has 3 orientations. Okay, it has 3 different orientations. So the first orientation can be the x orbital, and to just draw a dumbbell shape, we will draw 2 ellipses, and then we must make sure that the center is in the origin. It's drawing half of a chromosome, if you're familiar with it. This is what it looks like, and this is the px. So this must lie on the x-axis, right? And the node, the center, must be on top of the origin. And this is how we draw the py orbital. It must lie on the y-axis, as you can see, and the center is on the origin. And this is a different kind of orientation. It is the pz, and it is going to be lying on the z-axis. This is how we show it. And this is the dumbbell shape, and it is actually the shape of p orbitals. And the spherical shape is the shape of the s orbitals. Okay. So now I will be continuing with electron configurations. So we learned how inside an orbital we must have a maximum of 2 electrons with opposite spins. And electron configurations actually have 3 different principles, and the electron configuration of elements obey these rules. Okay. So here, let's take an example of the Pauli exclusion principle. So it states that an orbital can hold a maximum of 2 electrons with opposite spins. In the s sublevel, we only have 1 orbital, right? And in this orbital, we can only have 2 electrons. So this is what it looks like. Let me show it in the orbital diagram here. So we have we have 2 electrons, and as you can see that the arrows point opposite ways. So this shows how they have opposite spins, so that they don't repel each other crazily. Okay, So this is the Pauli exclusion principle. It states that inside an orbital, there can be a maximum of 2 electrons and they must have opposite spins. Yep. And it's also the same thing with the p sublevel. Let's take a look at the p sublevel. It has, let's occupy it, 1, 2, 3, 4, 5, 6. As you can see, inside an orbital, we have 2 electrons and opposite spins. So this is another example. Okay. And another rule is the Aufbau principle. The Aufbau principle states that electrons occupy lowest energy orbitals first. So the orbitals are actually filled in order of increasing energy. So when we're actually drawing this diagram, let's say that we're drawing for magnesium, right? And it has 12 electrons. Okay, so let's fill this diagram according to the Aufbau principle. So it will be filled in order of increasing energy. 1, 2. Okay. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So, as you can see, I actually filled them in order of increasing energy. I started by filling the 1s orbital first, and then I finished with the 3s because the 3s has a higher energy than 1s, and the Aufbau principle states that we must fill the orbitals in order of increasing energy. So this is how we do. You start from the bottom, you go up to the top. From bottom to up, okay? This is the Aufbau principle. And here you can see how you must fill the orbitals. By the way, there's an important piece of information that we must always remember. S orbitals are actually, as you can see like in the diagram, S orbitals are actually lower than 4s orbitals are actually, the 4s sublevel is actually lower than the 3D sublevel in the orbital diagram of electrons. And this is like the same case with 5s and 4d. So s is filled before d. Okay, so that we can take a look at this. 4s before 3d, 5s before 4d. For example, 6s before 5d. So this is like the order. And the final rule is the Hund's rule, and it actually states that electrons fill each orbital before pairing. So I will be showing this with an example. We have nitrogen and it has 7 electrons here. So let's draw its orbital diagram. Okay, let's do its electron configuration on the orbital diagram. Let's say 7 electrons. 1, 2. Okay. 3, 4. 5, 6, and 7. Okay, so did you realize how I did not doubly occupy one of the 2p orbitals before? Because we must fill the orbitals separately before we doubly occupy them. So for example, if we were actually drawing the electron configuration of the element with 10 electrons, this is how we would draw the 2p sublevel. The electrons in 2p sublevel 1, 2, 3, and they're now singly occupied, and then I will be doubly occupying them. So instead of doing such a thing, like for example, if we want 10, not 10, we have 4, 4. If we want 6 in the 2p, so this is not what I do. This is not a correct way of showing it. You must fill the orbitals singly before doubly occupying them. So single before doubly occupying them. And this actually minimizes their repulsion. Okay, electrons fill each orbital before pairing. So this is the Hund's rule. These are the rules for electron configuration. Okay, so now let's do a few examples from electron configurations. Okay, so maybe I could do, as I already did magnesium, I could do phosphorus. So let's draw its electron configuration. Let's state its electron configuration has 15. So 1, the first main energy level, we only have the S sublevel here, and it is filled up 1s2, and then we move on to the second energy level, as the first main energy level only has the S sublevel. So this S sublevel will also be fully occupied. And then the P sublevel in the second main energy level, which is the second type of sublevel within it, will be fully occupied. And now we have 10 electrons, and then we are done with the second main energy level. And let's move on to the third one. It will be 3s2, and now we have 12, and we will have 3p3, right? And let's draw it. So 1, 2 here, 1, 2 here, 1, 2, 3. As you can see, I'm like placing them in separate orbitals. 1, 2, 3, 6, and like this. 1, 2, 3. Again, you can see how Hund's rule can be seen here. This is an example. With phosphorus, we did this. And for example, let's take a look at, for example, an anion or like a cation. Let's do a cation. Or let's do iron. Let's skip this one. Okay, so iron. Oh, it has 26 electrons, so 1s2, 2s2, 2p6, we have 10 now, 3s2, we have 12, we have 3p6, we have 18, we have 4s2, as you can see, 4s2 before 3d, and how many are there? We have 8, 10, 16, and 4, if 16 and 4, and we have 3d, 6, as I believe, 2, 4, 10, 12, 18, 20, 26. Okay, so this is the electron configuration of iron when it is in its neutral state, right? It is not a cation or it's not an anion, so it has electrons so electrons weren't removed from the outermost energy level in order to form a cation, or like electrons were not added to the outermost outermost energy level to form an anion, right? So it is neutral. And yep, and it's also a transition metal. It's kind of important. Let's take a look. And we filled S first, right? We get filled for S first. And let's remove 2 electrons from it to form a cation. And in transition metals, when forming cations, you must remove electrons from the 4s sublevel first, although it's at a lower energy level than 3d, but it is in the outer main energy level. So let's get rid of the 2, and this will be its electron configuration. Okay, so its new one will be, let's actually draw this one. So 1s2, these have been removed. 2s2, 2p6, we have 3s2, 3p6, and 4s2 is actually empty, and 3d, 1, 2, 3, 4, 5, and 6. So this is going to be its electron configuration in the orbital diagram. Also, you can also do like full and condensed electron configurations. So we basically did the full ones here. These are the full ones, but for the condensed electron configurations, we must actually look at the configuration, the electron configuration of noble gases as they are stable. So basically group 18 elements. And we just use this to simplify the notation. For example, we can do this with phosphorus. Let me take a look at the periodic table. And I believe it's neon, but let me just double check. Okay, so we have neon. And neon has the electron configuration of 10. It has 10 electrons and 1s2, 2s2, 2p6. So these are going to be the core electrons, right? And then on top of this, we're going to just add 3s2 and 3p3 for phosphorus. And you can just denote this like this, neon, just put the symbol in close brackets, and then you can just say 3s2 and 3p3 for the condensed electron configuration. So you must just find the preceding noble gas. So basically the noble gas with a smaller with basically the preceding noble gas, and you must like replace and the inner electrons of the element with the symbol of the noble gas as its electrons form the core, and you must just add the valence electrons as I did in this example. So this is how you do the condensed electron configuration. We have two exceptions to the Aufbau principle, and this is like the final part of the electron configuration part of the structure. Okay, so we actually have chromium and copper. Okay, so normally this is like the number of electrons. So you would normally expect chromium to have this electron configuration, right? But this is not the case. Oh, I think I might have wrote it in an incorrect way. Let me just check. I guess, yes, I did. Okay, I obviously. Okay, it has 6, so okay, now this is correct. This is what you would expect from chromium according to the Aufbau principle. The lower energy level would be filled first, and then you would have 4 additional electrons in the valence shell of 3D in the 3D sublevel. But this is not the case because this actually makes the element, the atom, unstable. Anyway, this is like unstable. We don't want this. So instead, this is the electron configuration. So here the 4s sublevel is partially filled, and it's the same with 3D. It's also partially filled. As you know, it can hold a maximum of 10 electrons, and this one can hold a maximum of 2 electrons. So basically they're partially filled, they're half filled, and this actually makes it more stable. So when they're half filled, repulsion is reduced, so it's more stable. So this is actually the electron configuration of chromium for S1.3D5. It doesn't obey the Aufbau principle that states that we must fill orbitals from low energies to high energies. Anyway, and a similar thing happens with copper. As you can see, this was what we would expect, but this actually makes it unstable. And so instead, 3D10 is fully filled, and this is half filled, and this is a more stable configuration. So these two examples are super important. So yeah, this is the electron configuration part. And now I will be explaining the HL extension topics of structure 1.3, ionization energy and successive ionization energies. So let's start with ionization energy. Okay, so this is HL only. Okay, so now in a line spectrum, we know that as energy increases and as frequency or energy increases and as wavelength decreases, we know that convergence occurs. At high frequency or energy, the lines merge, right? And this is actually the limit of convergence. And basically, it happens in the emission spectrum when frequency of emitted photons increases and the spectral lines actually get closer together. And this is actually called convergence. So at highest frequencies, the lines merge into a continuum, and this marks the limit of convergence. And the limit of convergence actually corresponds to the energy needed to completely remove an electron from a gaseous atom, and this is actually called ionization energy. So it corresponds to ionization energy, and the exact definition is minimum energy required to remove an electron from 1 mole of gaseous atom in its ground state. So we must memorize this. Yeah. So the limit of convergence corresponds to ionization energy, and by using these equations, we can just calculate any of these variables. And also, the trends are included in structure 3.6, but this is already explained in 3.1. So you can refer to the video, and so actually more details. So this is why I didn't include the explanation, because it was a really tiny part and it wasn't even detailed. So as I mentioned, you can just use this information to actually find any of these variables by using these equations. And now let's actually move on to successive ionization energies. Okay, so first ionization energy refers to the energy needed to remove the first electron, right? And ionization energy was the minimum energy required to remove an electron from 1 mole of gaseous atom in its ground state, right? So the second will be the energy required to remove the second electron. So like the first one, energy required to remove the first one, second one, energy required to remove the second one, the third one, energy required to, so this goes on for a while, right? And this is how you can actually represent the process by the equation. Here you can see our element, it is in the gaseous state, and when you actually basically when you actually add the ionization energy, it will become, the gaseous atom will be ionized, and it will actually you will be able to remove an electron, so an electron will be removed. So this is the first ionization energy, and for the second one you will use the ionized element here. This is why it is a cation, and when you add ionization energy, now you will have the element ionized twice, so this is why the charge will be 2, and you will again remove the second electron. So this is what it is. The second ionization energy is basically a successive ionization energy. Okay, so but these like successive ionization energies always increase because as we remove electrons, the remaining electrons experience a strong electrostatic attraction to the positively charged nucleus, because the nucleus is positively charged. So let's say that it has plus 12 charge, right? So let's say that it has plus 12 charge, and normally a neutral atom would also have minus 12 charge from like its electrons, right? But when we remove one, it will have now minus 11 charge. And now as the magnitude of the nucleus of the charge will be higher, there will be a greater electrostatic attraction. So in order to overcome this electrostatic attraction force, the ionization energy must decrease because you require more energy to remove an electron now. And we can actually use the data of successive ionization energies to deduce the group number of elements. And this is actually done by identifying the large jumps. So for example, here we have some data. The first ionization energy was 500 kilojoules per mole, and second was this, second one was this. And as we can see, the big jump occurs between the first and the second one, right? And we know that, and we can actually conclude that the first electron was removed from a valence shell, because now, as it has been removed, you're getting closer to the nucleus. So this is why our ionization energy is increasing, because as the valence shell electron has been removed, because electrons start getting removed from the valence shell, and as we move on to the inner shells, inner subshells, more energy will be required because the inner subshells are closer to the nucleus and the electrostatic attraction is increased. So more energy must be required to remove an electron because the attraction is really high, right? And this is how we can deduce the group numbers. So the first electron is removed from a valence shell, so we can say that it's in the first group. So for example, this could be, for example, lithium. Let me show you the electron configuration of lithium, 1s2, 2s1. So for example, we can just say that, I'm just giving as an example, this could be another element, but I'm trying, but it can't be hydrogen because it only has one electron. Anyway, so let's just get rid of, let's just remove one electron from the valence shell. Goodbye to the 2s electron, and now we have 1s2, right? Our electron, the next electron will be removed from the 1s sublevel, right? And this is really close to nucleus. So more energy is required to remove our second electron. As we removed our first electron from an energy level that is further away from the nucleus, we required less energy because there was less attraction between the electron and the positively charged nucleus, right? So now the ionization energy was lower. But now as we move closer to the nucleus, the ionization energy will increase, and the successive ionization energies will keep on increasing because the nuclear charge, the proton number will always stay constant while electrons are being removed. So the electron, the charge, the overall magnitude of the charge of electrons will decrease as electrons are being removed. So yeah, thank you so much for listening, and this was basically structure 1.3, including the HL topics, by the way. In order to find out more about trends, you can just watch 3.1 videos where trends of ionization energy has been explained in detail. And thank you so much for listening, and good luck with everything.